we're somewhere close to having a book that actually is functional. Last time wasn't really functional at all because all of the weird ass tables that my friend has actually notified me that looks weird when he was trying to read it, and it was like a pain in the ass to read it. So we start with calculus limit. Obviously, it's a super small stuff. Obviously, all of studies calculus is a small, small, small. And if you aren't really have anything about limits, then you're not really having calculus in your book. You're teaching nothing. You If you go jump to derivative, what are you teaching? You're teaching nothing because everything in calculus is about going really small, really tiny, and kind of projecting it to a larger set of continuous functions. Kind of. That's pretty much Taylor series. And honestly, in my college career, I mean not career, I guess it's college academic life, Taylor series and the Riemann sum have trumped everything in terms of use because they are easy, fast, and good to estimate. Riemann sum and Taylor series. What else have I used in calculus that's very useful? Um, I guess matrices. Yes, matrices are very useful. Mm, but yeah, but those are only useful for known stuff. Like basically, if you're gonna derive something, but most of the time I'm using Taylor's. I would use Taylor series because numerical method is the cream of the crop when it comes to real life analysis. I think. Anyway, we're going to very small things. So over here we have slopes, which basically I should probably not talk too much about it because actually no, it's fine because first thing is just an overview of the general basics of what we're gonna learn, but basically you're not gonna actually know what it is pretty much. And I put the formal definition of limit here, but nah, there's no way they're gonna learn that one. Know that one yet. And then discontinuity is where we start off because every single time I went to, I think calculus one, which is AB, calculus cal AB, I learned discontinuity. One thing they don't teach you in AB is this type of discontinuity, which is oscillating discontinuity. Um, very. I don't know the use of this. I haven't used this ever in engineering. There's a one-sided limit, which did I ever use a one-sided limit? Not really. I've never used it properly. I don't think, at least in the math sense. Oh yeah. So we talk about limits first, although because that's all of calculus. So I'm just gonna move on because that is limits. Um, then I talk about derivatives, and I love deriving these things because it pretty much I think it actually teaches you everything you need to know about calculus for a long time. That everything is part of limits. For example, but I think the way they teach you, depend on the professor, would be better off if they teach you the proof. Because certain proofs like the chain rule, I didn't understand until I have a because chain rule. I don't think I understand until 20E actually. Because in UCSD there's 20A, 20B, 20C, 20D, 20E. Um, and I didn't understand what chain rule was until 20E because 20C was where I actually formally kind of understood it, but I didn't understand it from 20A actually because 20A learned in high school, but I really didn't get teach. And I think the problem was I didn't have the proofs. And once I realized the proofs, it made sense. But I get it. High school uh, students, I don't think they would understand the proof if I even gave them it. So, especially since the only proof I think I did in high school was this one, which is completely like, wasn't really helpful to me because it didn't really prove the power series to me. And this was the proof I was learning. I didn't really do the power rule. I do the power rule now, but I understand why you wouldn't want to do it in high school because it's a lot of algebra. Moving over here, this is painful because you have to know you have to get these formulas first of all, and then you have to realize that if you move this out, you have this inside over here as part of this, so you can actually move the x end out over here, this x end, and then this one because he has over here one over here, so this is one over here, and you have negative one over here, and that basically is the basis for this equivalency. And then yeah, you also need to know about this, which basically means that if you divide everything by an, you get an, and then an out, which means you get this from the finally. Um, Oh, because I changed this thing to a big X. Because big X would be a nightmare to put this copy and paste this everywhere. So I just said big X would be what we put down. So when we do that, we realize that this turns into this, basically due to I forget now. This part is this, right? And then we move this one out. So we did this minus this. So we moved this thing over here, and then we minus it to get this part. And we go down over here, and now we plug it back in. We plug everything back in, and we realize that we plug everything back in from to over here, and then we realize we have an over here, so we multiply an both sides, and then we have this function, which we pluck out the a out to get a over here, so we can cancel out a over here, so we get this finally, and this gives you this. But we know another definition of derivative is this. So we're using that definition because that's easier. So um, we can see that this is replaceable over here on the top. So we replace it over here, and we realize that this can be canceled out over here, this one, and then over here, this one. So it got canceled out to get this. And you see that there's an A over here, so we can plug X as A, because if you in limits, if you can plug it and get something out, you're done, as my high school teacher would say. Which yeah, over here you get an over here all the way over here, and you can see that there's if you look here, multiplied by a n minus 2 dot 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 plus a n minus 2. There's a if you and then there's a square over here. This would equal a n minus 1, which if you look about it, this is, wait a second, this is just a multiplication, right? This is why it's n, because you just multiply. This is like a summation. Actually, there should be, I mean, I might want to make another step over here where I kind of show what I mean, because in the future, in my future, I have used this a lot. I think it's 1, right? And then this equals to n, and this equals to an, and then this equals n because this doesn't have any I over here, so this just equals n over here. It's just getting a multiple of it. I don't remember if it's I equals 0 or I equal 1. I'm pretty sure it's I equal 1. Let me check. Because I equals 0 means you have something else in the need. So it'll be 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5, 6, and then you know what? Let me just get the mat over here and figure it out. It's very easy. I equals 0, and to n, we'll just say it's to 5. Then we have x0, x1, x2, x3, x4, x5, and then that's 1, 2, 3, 4, 5. Yeah, I'm right. It starts from I equal 1. Okay, so next I go to more limits on. Actually, I want to get the idea of infinity because infinity is a large concept. Because if you're going really small, there's always a possibility of going very big, and then that is need to be drilled in very fast in calculus, because otherwise you're gonna hurting a lot later. And there's a few part of calculus that I don't like for this one, because yes, you could get the e over here. This equals to e, and then you can get that as ln of e is 1. Um, so you can get this, but the problem is it's technically L hop, and guess what? To get this, you need to know the derivative of ln, and then if you actually try to derive and prove ln, you have to go back to this, and you're just getting a looping definition all around. So I have put up another definition over here, which is pretty bad definition in all honesty. Um, I tried to use epsilon delta proof to do it, but no matter what I did with epsilon delta proof, it didn't work out properly. It just completely made me want to cry. So I just stopped here. But I mean, if I figure out in the future, I'll probably put it here. I probably won't actually, because I'm not sure because this is pretty good. Just having it directed arrow over here and you figure out it's e over here ln. I think this shows a lot more because I did minus one over here. I did ln of this, so it kind of shows that it goes to zero either way. And then if you want the actual one over here, it's equal to e over here. So I think I showed it enough. But as you can see over here, even with the e to the x, we get this formula here, and you kind of need to know that it's e and one. Um, to get e of x to prove this. Um, and then again over here, I have to prove it over here. So I wish there's an epsilon delta proof that I could use, but I couldn't figure it out. I couldn't for the life of me figure out the epsilon delta proof that would work. So I stopped it for now. I'm not wasting more time. I wasted so much time on that this summer that it's kind of scary how much time I wasted. So I'm gonna stop on this. And this is for bank interest things. It shows that if this happens, it'll go all the way to E. It's not really that powerful, but I mean, yes, powerful for banking, I guess. But who likes banks? There's still things for. Oh, this is another looping definition over here. This equals zero over here, and you'll see why you could either use, I think, squeeze. Can you use squeeze? I think you can use squeeze to prove this. Actually, if you can use squeeze, then we're fine. Um. Oh wait, we can use squeeze, can't we? Okay. Did I use squeeze later on? Because I said it was a loopy definition because you need to use derivative, I think, on the top or bottom. So let me look over here. I did that. Oh, a chain rule over here I think is so important. The way they teach it, I don't like because they teach you in the first way, like D, F, D. They usually teach you in one of these. And this is a thing I have. I didn't understand chain rule because they never showed me a proof for A in AB at all. But I understood later when I was in calculus 20E, which I was ashamed of a little bit because you're supposed to really learn it in calculus 20A and 20 C. I got it again in 20C, but I just realized it was just delta F delta divided by delta D. If you don't know, in UCSD it's like 28, 20B, 26, 20D, 20E. So this makes sense to me in 20C, but you're not really understanding the proof definition until you get the proof. So I was told to do this thing where we go when you go like this and you go like, well, if you have df over here, you get dx over here, and then you get more chain over here, more chain over here. This weird graph. And then that's how we did in 20. See, I don't like how they taught that. I think they should just gave us the proof, which I think they did for 20A, but I skipped that. So it was kind of my fault. But eventually I said, you know what, I'm going to learn the chain rule. So I just said, yeah, I now understand chain rule properly with the proof. It's basically a lot of limits. Um, yeah, eventually. So I think that's very important for anyone to learn that. And then La Hop. Oh, I did use La Hop for this. Uh, do I want to change that now? Let me make sure I can actually do this with so it's 1 minus cosine x divided by x. That this can only be 0 1, right? 0, and it can be 0 to negative 1, and then that would mean this equals 2. Oh wait, does it go to infinity if I do this way? Yes, it does. Because it goes x over here, x over here. I see why I didn't do this one. Ah, yeah, that makes sense. And I get to 0. Yeah. The Oh wait, and this is over here 0, so 0 and infinity squeeze theorem doesn't work. That's why I didn't do it. Yep. Okay. I thought for a second I messed up, but I did not mess up. I was just looking at it and saying, "Oh, that looks possible." No, it doesn't. It's not possible. Okay, so we over here have the conjugates. Obviously, over here, this is a very famous thing they do in math class in 20A, which is AB, where they put conjugates in. I don't understand it because in engineering, I have never used this at all in my life. So weird. Yeah. If I'm wrong about something, please just email me. It's fine. Spam my email. I don't care. There's a filter, anyways. E of x equals to infinity. This is just I can prove it with S delta. I don't want to, because it's a pain in the ass. It's very much a pain. You can look it up, but it's it's much more painful than you would expect it to be. Um, so, I mean, later on there's a method. Yeah, I'm never gonna actually use that method because doing the EX is better just to prove it with pre-calculus and just say you know how that function will react and go to infinity, and how this goes to zero, and how this one will go to infinity. All of these infinities are not equal, though. Obviously, the exponential infinity over here is higher than the ln of x. This is obviously something from pre-cal, which I realize is not that obvious anymore. So let me go over here and show what I mean. It basically means this. This goes to infinity, but obviously this goes faster. The red E of x goes faster than if I were doing that one. So it makes perfect sense in that sense. And then we're doing squeeze theorem because sometimes L hop doesn't work. This, because of EX being EX, will just go on forever and forever. I think this was one of the questions, like one of the famous questions that made you pause and stop using. Oh, the hop works for everything. The hop does not work for everything. Um, yeah, that was a fun thing I figured out. Painful lesson I learned. Yeah, that was interesting. So we go down over here. We go to systems because systems are always something that you have, and then I think it's actually relevant for engineering. I don't know. I'm an undergraduate student, so who knows? Then we take a limit over here, which I think this is another law hop. I do a law hop. We could just skip down because it's a law hop. Uh, Especially since I have not used most of this for a long time. Imagined numbers always stumps people, but it's not really that hard. Over here we get delta proofs, which I finally figured out what it means. Basically, it basically means that over here, when you go to these things, this point, this side over here is continuous. This side over here is continuous. So it kind of makes sense that the ratio would be over here. It'll look like the same ratio. Um, the only when it's difference is when you use something like this, where you know that this is bigger, therefore you can just do this, which means that that bigger function over here, 2xe, the rate over here is good enough that it would prove that this would be continuous. Um, so this was the most interesting one out of all of them, in my opinion. And then we go on to more product proof. This proof I don't think was very, what's the word, hard. So I don't think this was something that, I mean, it was interestingly hard enough, but I'm wrong over here. I made a mistake. I think over here this is supposed to be gone. Yes, this is supposed to be gone. So it's supposed to be like that. Um, yeah, I don't know why I didn't take it out. If you didn't take it out, then it's a weird function. The other quotient rule is more interesting because quotient rule is a lot more painful to actually figure out. I wish they actually proved this in AB, but they don't really prove it. They just tell you to use it. I don't think I ever got a proof for that. So yeah, we got a proof. Oh yeah, this thing. Ooh, that was that just shows the differentiability of that. It's not really that impressive. Um, it's just something you have to do. Uh, More interesting enough is the, where is it? Well, it's just yeah. Oh, Riemann sum. Yeah, Riemann sum I always love, but the most interesting part of that is when I actually got to prove this shenanigans. I always wondered, could you use different integrals and you prove it? Yes, you can. You can definitely do it. You just need to know what this turns into, which is something like that. And there's some kind of rule that I want to eventually figure out, but I'm not figuring it out right now because that's I saw it and then I think you can prove it with factorials, but you don't need any calculus. But it's a pain in the ass. I remember something like this in where was it again, in AB or BC, but I forgot to do it. So I'm gonna try to figure that out later. Um, anyway, we just bring into more calculus and then more of this proof thing because there's a lot of properties of integrals which I never use in engineering. Funny enough. So we get the second problem. Yeah, that's fun. And then, oh yeah, that's the area average. That's no fun either. I never use that. I use this thing a lot. I use the mean value theorem. I never use the average a lot. I mean, I use it for Fourier series actually. So I actually take it back. I used that one a few times, I guess. And I use it for fluid analysis too, right? Because fluid analysis, you get some kind of turbulent flow, and you want the very perfect line. You would use an average theorem. Um, Not the way that they taught you in calculus, but still average theorem. A differential equation is kind of important, but the way they teach you is kind of useless in real life because you would need to use differential. I guess it gives you the idea of what a finite numerical method version of it would be in the end. So I guess I have to give it to them. It's very useful. But I there's also another differential class later on, anyways, because they teach you in AB, but they reteach you it in 20D again. So yeah, what was this? Oh yeah, I remember this one. Basically, it was getting an absolute minimum and absolute max and max. Yeah, this was not that painful. I remember that one. Oh yeah, now we finally actually get into the integrals that are actually pretty intensive. Not really that intensive, still doable. The fancy use stuff is a little weird. I like the trick stuff, but I don't like the way they teach it because trick stuff is usually taught by doing following the what the book says and get the answer. When there's a way to derive each and every one, there's actually four answers you can get, which all equal the same thing, which is pretty cool with different plus C's. And I just realized, did I not write plus C's here? Fudge. This shows how bad I am because you always want to do plus C, and I'm glad I saw it. I'm not rewriting this into with my notepad and doing it. I'm just gonna go with the cheap method, and then with the this method, and cover my butt this way. I'm not actually gonna do it this way because they're not equivalent to each other without the plus C. Um, because let's just show it. I think one of the question was that I made a question about that same thing. Um, Here, I think that shows it. That wasn't the one I want. Negative. Shows how there's a pi divided by 2 difference of this, which is the reason why there should be also a negative somewhere. Oh, yeah, this one is a negative over here. I did plus C over here, but I didn't do a plus C over here. Weird. Must have been losing it. Uh, oh, wait. Oh, I see why. I see why. I'm dumb. I'm dumb. I actually did it. So basically, these are not the solution of this. This is over here. So can I make a finger point over here? I don't know. What I basically did, let me put the arrows over here. This is given by the trig over here. This is given by the trig. This over here is given by a function. I chose one of these two and put it here. I thought I made a mistake. No, I didn't. I'm fine. Not that. I mean, wasn't that bad. All right, and then I was just proving again that they're the same equivalent no matter which method you use. So sometimes you get four of them because of how arcsine and arccosine works. Some of them you only get two ways, and then two ways give the same answer anyway. So whatever. Um, yeah, and then I just kept on going, kept on going. Oh yeah, integration by parts are so interesting because I used that a lot for was again for Fourier series. I just wondered like it was very useful. Let's just say that. Um, So yeah, I did a bunch of that over here. Did a lot of triangles. Did a lot of triangles actually. I thought I'll do a little less. Um, yeah, then we start to prove the integrals of sec because it kind of was interesting. I was always told this, but I never got. I'm not sure if I got proof. I think maybe we did. But the more interesting proof is this one because this one is really weird over here. When you look at the absolute over here, you get equal to it should be equal to one, and then you get negative one over here, which I was like interesting. That's how you get the property of this, and I was just like, huh, you learn something new. I would never expect that's how way you can actually do that. And then there's more intuition with parts. Yeah, and I had there was a time where I was very interested in integration by parts because it was very interesting. Um, here's that question about the pi divided by 2 over here that you worry about. And if you have something, and I believe the other, if you did the other way, the other functions like over here, um, like plus pi over 2 or something, I don't remember. um, and then we go into this, which is basically going to vector, like going change in x and change in y, depending on time. So you can look at the 3D thing over here. If you were actually to graph it, I would graph it in 3D because x, y, and then t. And then you'll see how, if you did the differential over here, you divide them, it's just chain rule. Honestly, describe a chain rule is better than what I described it. And then we go into more of this nonsensical talk. I'm basically showing how I actually changed from my beginning state, and I think my textbook has become way better because I have actually a clear direction, like what to do, A, B, C, D, E, F, G, in my own head. That drives what I'm doing here. And then we talk about the cosine h, which I think is actually kind of weird. Anyway, partial fractions is one part that I always use a lot. Don't like the way they teach it over here. The limit method is so much better because it's better for computers. In my personal opinion, the limit method is fast um, when you're doing code, which right now nowadays that's how we're going. So we should probably teach a limit method, in my opinion. But either method is intuitive enough. And then, oh yeah, imaginary numbers, complex numbers. This was so interesting to me because in BC I didn't get taught it, but in 20B I did. So it's something that I think that um, if you're gonna skip 20B, I would study this again. I would study this because kind of interesting. Kind of starts your idea of superposition. Um, it's not the hardest thing to do, although it's pretty simple enough. And then we go to solid. I need to do more of these questions, but the most interesting is Gable's horn and nothing else. And Gable's horn, everyone kind of knows about it. And then yeah, that was next part is Taylor series, which this is the funny part. I got taught summation test before Taylor series, and I never liked it because I don't think we even got taught how to do an integral with Taylor series. But the convergence test over here, which oh, this is too big. This would, if I were to, uh, yeah. Convergence series is figured out by ratio test or the root test or power test. One of these tests to figure out, and then you just drag out the x because x doesn't really matter over here. Sometimes you can't because it's x squared over that, and then you have to just prove that um, whatever variable goes. It basically is. Greater or less than something like this, when the x square like this, you just have to figure out how to do the square root over here, square root over here, or square root of n over here, and over here, and just take the limit of that. If you have something like x square root of n, um, but you can also see something like this happen where you can just get rid of it if everything is square, so you can try to do that too. Um, but I like Taylor series first because Taylor series is the reason why you have this submission test, but you always get submission first, which I never understood. I never liked it. But I do understand that I need to talk about the only valid part with the IOC, which I don't really tell you. But in all honesty, I have never used the IOC. I mean, I have used the IOC, but you know, some of the IOC is kind of weird. Like Arctan has like IOC of pi divided by 2 to pi divided by 2, even though it's continuous. And I don't know the reason why. I mean, I kind of do know it's Arctan after all. And if you want to get the infinity version, you have to go, I believe, all the way into infinity and do a Taylor spectrum from infinity, which is kind of weird. But that's how you do it, I think, if I remember correctly. So I love Taylor series because I used to hate it, but now I realize it's super easy and it's like very good at estimating for certain distance, like short term. Um, and the integral is not that bad. You're just doing polynomial estimation. Sometimes it's bad when you're doing something like arc. I believe is integral of tan. It becomes a pain, something like that, where there's a discontinuity and you just get imaginary numbers and it just doesn't work out. I tried it, doesn't work out. Don't try it. So yeah, you also get to prove the Euler's famous formula. I forgot what it's called. Uh, it's very interesting how I never got taught this actually. I always was told this, but the funny thing about calculus is that when I got taught this in trig, they expect you to know it, but they never prove it to you afterwards. And when you go to calculus to prove, and they never prove it, they just show it in. So I tried it with arctan, no tangent tan, and it didn't work out because it's good. It gives imaginary numbers, and it was a pain. It didn't really work out. Tried to do integral of that. Um, Never do that again. Um, but I did figure out something interesting with it. So if you do it this way, you can actually get all of this with just this polynomial, um, which then can be. I think you could try to do the integral of that because it's all continuous over there. But I would try to do a Riemann sum of it, and I would do an H. But I was not gonna do that. I was too lazy to do that. And I knew there was the way with hyperbolic functions with the partial fractions. So I was saying, yeah, I'll do that later. I haven't done that actually. I left it alone because it was a pain to do. So we'll do that later. And then we start with vector, which is basically the idea of what was it called again? It was the physics with the G thing was that you could change in one direction with dt and change with dt in the x direction will be different for both of them because the acceleration is different in those things, and you can split vectors into two basically, which is actually taught in trig but reinforced with calculus, I guess, and not really. And then we just stop with it. I should probably add something to here, but we also go back into this again with multi-calculus, so it's not really that big of a deal. And then we go to summation, a lot of summation, in my opinion, because now you have once again Taylor series. You have a reason to do this, but I really don't care about summation too much. I don't know. I like summation, but I don't really care for the convergence test that much. It's kind of there. We use it. Everything except for the ratio test I haven't used. So I don't know. The ratio test is the most important. Everything else is kind of squat. Um, Polar form, I the way over here is actually just half r squared, and I actually kind of proved why that's true. So if you don't have any other function, if you don't have a function of g and r and theta, just have a equation with r theta. You don't really need to have it that way. You don't really need the g of r theta. You can just have r theta, and you can see over here with the Jacobian matrix later on. I didn't really talk too much, but you get r dr d theta, and that equals this formula over here, which is the actual, in my opinion, the better proof than the geometric proof over here. I like this proof better because it kind of shows the actual version versus the simplified version where only theta is to change. Um, this equation over here will not be integrated by that. Anyway, so yeah, and then I just threw a bunch of questions that I completely don't care too much anymore, but I used to care in the past. But the thing is, engineers never use this. I never, at least I don't think I have never used it in my life. So I think we use it for ellipses for like planetary bodies, but I have never used it for something like this. Like, what is that shape? I never used that shape, so I don't know what to say about it. Other than, yeah, it's a very interesting question, but in engineering, I never used it. And then this is the only thing I have kind of used, but I think there's an easier way that we have. So that was a pain for no reason. And then we go to here, which I don't think I've used, and then we find, and here's the arctan that I was gonna start but never finished, so nah. And then here we go to 2D limits, which is more in line to what I need to do. And then I stopped here. I need to do more. I'm thinking of doing another section, a whole section on planes, because the plane, for some reason, was important. I haven't really used it other than orthogonality and then the orbital bodies. So it kind of has its uses in 120, 180, MA 180. So yeah, this is where I am at. As you can see, it's much more clean, I think, in my opinion. And you can see that from all the way up over here. It used to be a lot of boxes, but all the boxes are pretty much deleted. Um, Except for in this near the start where I talk about language and the difference, the connection of math and language, kind of necessary over here. So kind of need to add that. Oh, what happened here? No, we're fine. And also a lot of the handwriting thing, I cleaned up. If I took a picture of something, like I used to take a picture of something I drew and put it on here, but I deleted all of those because it was kind of like, why do I have something so unprofessional in there? So that was change. Yeah, that was interesting. Yeah, yeah, I was. Yeah, yeah. I heard that one of my what's the one of my a fellow student one of the campers in Cosmos, asked someone, and then he said that this is not true, which is okay, fine, fair enough. I find it true because they said, yeah, it's square, but it's not analytically true. But I find it's true because if you look at it, it's a square, it's a square, and I don't care what people say. It's just a square. At that point, if you go to infinity over there, so that's my opinion. This one, maybe I should delete that. I don't know. Kind of questionable. I don't know. Anyway, yeah, this is domain. Yeah, as you can see, it's much cleaner than before. I think it's a usable book now. Before it was unusable, pretty much because of all the messiness and all the unorganization. But up to calculus, where I do multi, it is cleanable, so it can be used till BC finally. So that's useful, I guess. Is useful to A, B, and B, C, and anything before it, except for statistic. I have gotten a statistic book to read, but I have not because I forgot most of the statistics. So this book is what I'm going to use to remember myself, remind myself all statistics. But I just don't want to read it, so I haven't been reading it because statistics sucked the life out of me before. So I don't really want to touch it ever again. Um, to be fair, it was because of my incompetence, but yeah, it's actually very much due to my incompetence and my laziness that happened. To be fair, to be honest, because I'm lazy. I know, I know. Yeah, it's pretty much cleaner. I don't know. I have to thank that guy that told me that it was a really mess of a thing, and I've focused on more on what's the word proofs than anything else, and the questions with answers. As you can see, none of the questions over here has no answer. Literally has the answer right next to it, right below it, all of it. None of these questions have a question that is not below. And there's an approximation here, which I think you could use for something, but I don't remember why. Oh yeah, I don't. Oh, I think it was to get to infinity. And yeah, I think 180 taught you that it was the point of infinity, which taught you if you're doing a celestial body, blah 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 blah. And but if you're doing a celestial body, you wouldn't use rectangular. You would use polar, and you would use special polar because if you did a hard polar, it becomes a complicated equation. Yeah, that was true. Because if the less complicated you get with the same amount of information, the better it is. If you have a complicated method of doing it, it just is bad. No one wants to do it. Math is about simplification sometimes. Sometimes about finding new ways to look at things, which is this one. I never thought of imaginary numbers as something like a thing that you can use for absolute value. But now thinking about it, I should probably have thought of that because um, the definition of absolute value with imaginary is a squared plus b squared square root, which really makes sense with what happened over here, which all the circle variables valid over here with the imaginary solution. It makes perfect sense. Yeah, and then yeah, there's a lot of absolute value shenanigans that makes it really hard. And then I have revamped the how I would show off the shift. I realized before I didn't really show off the shift that well, so I have done that over here. But most of it I have actually done it properly, I think. Um, and then we go more of that. Yeah, that was interesting. I flip flop from this to this because at this time I think you need to handwrite it. So sometimes I would do handwriting, make it look handwriting-ish because I thought that you kind of need it. And this is where I say, oh yeah, this was something I added because I want to show the difference very well. Like I want to show it like right there. So I just did a bunch of them. I said, yeah, that makes sense, right? Kind of look complicated, but it's pretty simple. Anyway, sketch again. Um, I really like these sketches. It shows that the kind of like the human element of it before I used all of the digital calculus. Because in reality, I don't think I have ever did a drawing by hand since algebra one, or algebra two. I don't remember. I think algebra two. I've done it with a calculator all the time. Actually, I take it back. In calculus, I did it a few times in Cal A, B, and B, C. But after that, in college, all graphing calculator, baby, which is why I got a really good one. Actually, not really. I just broke it. Fun fact: I've broken my original TI 84. I've broken a phone before. I've broken a computer before. I've broken um, what was it again? A DS, 2DS or 3DS. I broken a Wii. I break everything. I broke so much things. I think it's actually 3DS. One of them was a DS Plus or something. I forget. One of them, I don't know. I break everything. It's a fact. Yeah. In school, I broke like a bunch of things too. Like for example, the beaker. I didn't read the instruction. I burned a hole right through the bucket, which was very interesting. I learned that day to follow instructions. That was high school. I follow instructions now, very much so, to the point that it's kind of weird because sometimes you just want to starve. Yeah, except for when it comes to electricity, because when we're doing circuits, we're so low volt that why not experiment a little bit? Um, yeah, yeah, right. I actually did horizontal and OP here. I did not expect that. Well, whatever. How are you sure about this? I don't know how I was so sure about this because you can't prove that, can you? No, you can. You can. You can definitely can prove that. Actually, you can prove that pretty much anything over here with the obstacle over here would be a obstacle like asymptote because it wouldn't touch any of the lines over here. Huh. So this is technically wrong. I mean, it's right, but it's also wrong because you have infinite amount over here. So the right answer would be horizontal zero probably. Um, Still right to say this, but that's oh, I also show more of these shifts because shifts are fun. They're easy to write also. So basic log was interesting because the way I showed this was with the log y divided by log x to show that if it goes to zero, it doesn't work. But then immediately after I showed this thing, which it might have, it's kind of confusing because when I show a negative over here, actually it's not that confusing looking at it again. It kind of shows what's happening. Oh, yeah, this is fun because technically, if you cancel out log log, you get a y equal x, but you lose information when you do log over here, where it's undefined over here. But technically speaking, if you do it analytically with math, you would show that y equal x and be the end of the call. So I wonder actually, can you actually prove that by log x over here, and then the absolute value? Does that change anything? Um, because that would explain a lot. No, no, no. It just made it worse. Never mind. It did create something interesting. But I'm not gonna touch that anymore. Oh yeah, right. Eh, kind of. It just shows more of the properties of log and different lights. I don't remember why I was doing this. I guess it was to make it easier to read. Yeah, that's pretty much it. Uh, oh, this is to show that log x squared does not equal log square, um, which I thought for a long time that they were true. So a lot of the things in calculus was wrong until I look at this and I had to change everything back. That was fun. Um, yeah, then there's a shift over here. There's a few shifts actually, and then there we become to calculus. No, not calculus. We go to geometry here. I love geometry, but that's this proof is kind of awful. But we keep on continuing with geometry, which was the start of the unit circle, which was the start of pain, honestly. Um, it was the start point, yes. And then we just showed trig identity of here. We could have shown it through analytics. I think we proved it here. Yeah, we proved it here, but we could show it through another method. But I don't think I did, which is good enough. I don't really care, because I should have two methods is fine. Um, we definitely. Oh yeah. Here's the calculus. I didn't want to actually prove it through another method. I think there's a method with a cylinder. Um, because it's a pain in the ass. So the easiest way would be just doing calculus. I just said, you know what, we're going to do geometry with calculus over here, and then we're not going to actually put it over here in the calculus section. So if you want to know the geometry proof, go to the geometry proof section and figure out what that is. And then we go, yeah, and that's pretty much what I said and did. Oh, the symmetric property. That was a lot of pain. I don't want to look at that anymore because I never use it ever again as soon as we're done with it. Um, yeah. We go to imaginary, and then we go into block, and then I use a Jacobian matrix, which is kind of off, but it's just to prove that the area of a circle and the circumference of a circle, pretty much it. Um, Not really that difficult, in all honesty. We did prove the 4 divided by 3 pi square. I think I'm gonna make another big update like this probably when I'm done with the physics section because oh no, I'm finished with the rest of math, and then we start with the physics section, and then we'll talk again like this again with a big update probably. Um, yeah, we prove that. We prove this. Oh, bisexual divided by 2 pi. My geometry is not really that great. I guess that's pretty mediocre in my opinion. Maybe I should delete the highlights. People don't. I was told by my friends that no one likes the highlights, so I'm deleting them all over the place. But in this case, I think the highlights were needed. Never mind. I only did one proof because this was the vein of my existence for all of geometry honors. These were easy, but they were just painful. I never want to touch these again, and they were never useful for me as an engineer, um, except for problem solving reasoning, which is all I use it for. So never use it as an engineer. So I don't know what to say about that. We go down over here, and then we go with the pie question because also everything is public domain, so it's kind of funny how I did this. And then yeah, donut, lovely donut. I could totally take a picture of that and probably put it there, but I didn't, so they get credit. Over here is a big ass proof. I decided to do it in a drawing because it's much easier to prove. Um, yeah, in the end, it kind of makes sense to me. It's actually way what's the word eleganter than I thought. I thought it would be way worse, but it's not that bad. And then we go to the proof for the area of the triangle, which is this. I never made a question because I never really used that ever, so that was interesting. Um, we'll start with an interesting ECE question to get something like this. Um, I think there's a few more solutions, but for engineering perspective, this is the only important one. Every other one is trivial. So that's the most important one. Everything else is trivial, so we don't really care, I don't think. We go over here with Sakatoa, which was very useful. We'd be interested again. Which next we just go with the graphs and show all the different properties of it. The one thing I'm proud of here is not these. These are pretty fine. Let me look over here. Oh, this was very intensive. It took forever for me to understand what this is. And I forget it. After you prove it, yeah, I prove it to myself, and I can just toss out that proof forever. So I know this now. So what does that mean? I never have to look at this again, and I can with confidence say that this is true without bullshitting myself. I can say with confidence that this is correct, this is true, and I never will touch this again. I'll never touch this proof again. We're done with that proof. We're not touching that proof ever again. Same with this, same with this. Never touching the proof again. Uh exactly with the identity thing over here. So this is what I say. If you can't like just say that these are equal to your look at the proof, and once you prove it yourself, you never look at it again. You're done, you throw it away and throw it to the mathematicians that actually care. I do care. I love math, but there's a point in time where some of these math proofs go insane, and sometimes it's pretty much like, God damn it, what's happening? Like, there's no way to actually understand it sometimes, and then you just have to say, I understand it, and there's a way to understand it, but after you understand it, you just have to say, I understand now. I probably forget later after you understand it, so you just let it go. And that's why I feel about these big ones over here. And then we continue over here, which is with the simpler ones. This is not hard. This is just proving the square root of the thing. We're just continuing. We're just continuing, basically, and then we're just showing off arc second arc, all the other arcs, which fine. I'll also show the cursive method for the first time, I think. Cursive method I love, but it's not the standard way. My dad taught me this method, so I can't really say it's a standard. You just have to use cursive and see how it draws. You just say 1, 2. You end it over here. 2 goes on top, and then 1 because 2 is a higher number. 1, and that's how I memorize it. Very dumb antonym that I have learned. And then we got the other two forms, and I actually want to delete the highlight over here because my friend told me it looks bad when you have highlights, which makes sense when I'm printing this out. It doesn't make sense for it to have highlights at all. Yeah, let me delete these highlights. And okay, all the highlights are gone. Lovely. We continue over here. We go to all these unit circle shenanigans, which I kind of love, kind of hate at the same time because it's so confusing at the same time. But at a certain point, you kind of understand. You just memorize it. Arc sign will give you something like this, and we have a pi minus this, and then 2 pi n the end. That's kind of how I memorize these things because I know what to expect and what to get. Um, in reality, I've never used it beyond like plug into a calculator to get arcsec or arctan. I never get the 2 pi theory at all, so I never use that. So kudos. I don't know. We separate to the with vectors. Vectors are so useful, but I think I start with the and also another public domain picture. So yay! Um, we continue with this for a long time because vectors are useful and always are used. Um, Now I'm looking at this. I don't think I did a lot of questions with those, which I should have probably done. Uh, Instead of doing a lot of imagining things like this big ass thing that I don't remember. And then cosine h, and then I think we continue over here. What did we do over here? We did basically a lot of transformation, I guess, and then yeah, and then we do a one matrix question over here, which I'm not sure if I should have done, but I did. And then because I'm an aerospace engineer, I care a lot about these, so I put a lot of efforts on this one. Kind of, um, yeah, yeah. And it also showed how very unstable it becomes when you put it off center like this. That was fun. Yeah, I guess I put a lot of effort on that one. And then we do partial fractions over here, and then we finish off with factorials. Yeah, that's and as you can see, most of it is clean. It doesn't have any messy. So I cleaned it up all the way until multi-calculus. So I think I'm gonna the next time I make this kind of big update probably when I reach physics like A, maybe finish up halfway there. I don't know.